Hi to everyone who is watching this video. This video is about my course project under the Data Communications and the Networking 4. And for this video, we will discuss about the point-to-point connections and branch connections and access control list. Okay, so let's start. Okay, so point-to-point connections. This chapters covers the terms, technology, and protocols used in serial connections. The HDLC and point-to-point protocols (PPP) are introduced. HDLC is a default protocol for a Cisco router serial interface. A PPP is a protocol that is able to handle authentication, compression, error detection, and monitors link quality, and logically bundle multiple serial connections together to share the load. Okay, a WAN is owned by a service provider, and a LAN is typically owned by an organizations. It's like it's either what do you call this, ISP, or a corporation or a company, big company. So point-to-point connections connects LANs to service provider WANs and connect LAN segments. LAN to WAN point-to-point connection is also referred to as a serial connection or lease line connection. So lease lines are usually expensive. Lease lines are leased from the carrier. So companies pay for a continuous connection between two remote sites, and the line is continuously active and available anytime. Okay. Okay, so this is a typical serial parallel port 1. Typical WAN network. Okay, so one LAN is here and connected to, they are both connected to the service provider. So serial communications. Serial communication is a method of data transmission in which the bits are transmitted sequentially over a single channel. So equivalent to a pipe only wide enough to fit one ball at a time. So, multiple balls can go into the pipe, but only one at a time. And they only have the exit point, the other end of the pipe. Parallel communication. So bits can be transmitted simultaneously over multiple wires. Sends a byte, 8-bit. So 1 byte is equal to 8 bits. In the time that a serial connection sends a single bit. At one time, most PCs include both serial and parallel ports. Parallel ports were used to connect printers, computers, and other old devices. So which usually we don't use it anymore, I think, because we use universal serial bus. Okay, other devices that require relative high bandwidth. Serial and parallel ports. Well, on the most PCs, parallel ports are RS-232. Serial ports have been replaced by the higher speed higher speed, such as the serial universal serial bus. Point-to-point communication links. So point-to-point link used when permanent dedicated connections are required. So it provides single pre-established one communication path. So path goes from the customer premises through the provider network to a remote destination as shown in this figure. So you can see from here we have New York office and the London office. So each of them have their own network, and they're both connected to the service provider. Yes, service provider network. So they are connected geographically. So they are in distant sites, but they are geographically connected. So it can connect to geographically distant sites such as the corporate office in New York and a regional office in London. Not limited to connections that cross land, undersea, fiber optics. Usually more expensive than shared services. Constant availability is essential for some applications such as VoIP or video over IP. The bandwidth refers to the rate of which data is transferred over the communication link. So carrier technology will dictate how much bandwidth is available. This is what's commonly happening. Like if you're subscribed to a ISP, so they will dictate how much bandwidth you will have, depends on your package that you avail. Okay, so North America anti-carrier specification, European e-carrier system, okay. US optical carrier, OC transmission rates are a set of standard specifications for the transmission of digital signals carried on a SONET fiber optic networks. Okay. So these are the table of carrier transmission rates. Okay. Serial bandwidth. HDLC is a synchronous data link layer protocol developed by the International Organization for Standardization, or ISO. HDLC defines a layer 2 framing structure that flow and error control through acknowledgement. It's a default serial encapsulation method when connecting two Cisco routers. So Cisco HDLC is a point-to-point protocol that can be used on leased lines between two Cisco devices. Protocol field makes it possible for a single serial link to accommodate multiple network layer protocols. Configuring HDLC encapsulations. Use a Cisco HDLC as a point-to-point protocol on leased lines between two Cisco devices. If connecting non-Cisco devices, use a synchronous PPP. If the default encapsulation method has been changed, use the encapsulation HDLC command in interface configuration mode to re-enable HDLC. Okay, troubleshooting a serial interface. So here, how you do troubleshoot a serial interface. Okay. So command displays information specific to serial interface. When HDLC is configured, encapsulation DLC should be reflected in the output as the highlighted figure here. So encapsulation HDLC. Okay. So here you can see that this IP address is up. Means it's functioning. So it's yeah, it's a serial 000. Okay, troubleshooting a serial interface. Serial interface issues associated with the state on how to troubleshoot the issue. Okay. Status line. So, okay, let's go next. Show controls command output. Indicates the state of the interface channels and whether cable is attached to the interface. Okay. So here you can see the interface serial 0. And the hardware is GT96K, and it has a clock rate of 6400. So introducing PPP. PPP encapsulation should be used when there is a need to connect to a non-Cisco router. PPP encapsulates data frames for transmission over layer 2 physical links. PPP establishes a direct connection using serial cables, phone lines, trunk lines, cellular telephones, specialized radio links, or fiber optic links. PPP contains three main components. HDLC, like framing or transporting multi-protocol packets over point-to-point links. Extensible Link Control Protocol, LCP, for establishing, configuring, and testing the link data connection. Network Control Protocols, NCP, for establishing and configuring different network layer protocols, IPv4 and IPv6 control protocol. So this is a sample of HDLC and PPP connection. Okay, PPP includes many features not available in HDLC. The Link Quality Management feature, or LQM, monitors the quality of the link. LQM can be configured with the interface command PPP quality percentage. If the error percentage falls below the configured threshold, the link is taken down and packets are rerouted or dropped. PPP supports PAP and CHOP authentication. Okay, I think we will do it later. Okay, network, this, yeah, network protocol. PPP layered architecture. The figure maps the layered architecture of PPP against the open source interconnection or OSI model. PPP and OSI share the same physical layer, but PPP distributes the functions of LCP and NCP differently. PPP requires a full duplex circuit, either dedicated or switch, that can operate in an asynchronous or asynchronous bit serial mode. Most of the work done by PPP happens at the data link and network layers by LCP and SCPs. At the physical layer, PPP can use synchronous physical media such as lease line services, asynchronous physical media such as those that use basic telephone, and services for modem dial-up connections. LCP functions within the data link layer and has a role in establishing, configuring, and testing the data link connections. LCP establishes a point-to-point link. LCP also negotiates and sets up control options in the one data link, which are handled by the NCP. After the link established, PPP also uses the LCP to agree automatically on encapsulation formats such as authentication, compression, and error detection. So PPP permits multiple network layer protocols to operate on the same communication link. For every network layer protocol is used, PPP uses a separate NCP as shown in the figure. IPv4 uses IP control protocol and IPv6 uses IPv6 control protocol. NCPs include functional fields containing standardized codes to indicate the network layer protocol that PPP encapsulate. Okay. Just a minute. Sorry about that. Okay. PPP configuration options. Two compression protocols available in Cisco routers are Stacker and Predictor. Error detection identifies fault conditions. The quality and magic numbers options help ensure a reliable loop-free data link. PPP callback is used to enhance security. With the LCP option, a Cisco router can act as a callback client or a callback server. Okay. Next. So this is a basic configuration for PPP basic configuration. Remember that if PPP is not configured on a Cisco router, the default encapsulation for serial interface is HDLC. PPP is a layer 2 encapsulation that supports various layer 3 protocols, including IPv4 and IPv6. Okay, so this is how you configure PPP. Point-to-point software compression on serial interface can be configured after PPP encapsulation is enabled. Because this option invokes a software compression process, it can affect system performance. The PPP quality percentage command ensures that the link meets the set quality requirement, otherwise the link closes down. Percentages are calculated for both incoming and outgoing directions. Okay. PPP quality 80 is shown. The figure sets minimum quality to 80%, shown here. Okay. Multi-link PPP provides a method for spreading traffic across multiple physical WAN links. Configuring PPP requires two-step, as shown in the figure. Okay. So we have host name 3 and host name 4. So each host, okay, you configure You do the configuration. Configuring PPP requires two steps as shown in the figure. Create a multi-link bundle. Assign interface to the multi-link bundle. Okay, yeah, here we assign the interface. Okay, to disable PPP multi-link, use the no PP multi-link command on each of the bundle interface. Okay, so these are the commands on how to verify a PPP serial encapsulation configuration. Okay, so after you set up your PPP, you can go to each router and type in the command show interface serial and just indicate which serial port you use. PPP authentication protocols. PAP is a very basic two-way process with no encryption. The username and password are set in plain text. If it is accepted, the connection is allowed. Well, CHAP is more secure than PAP. It involves a three-way exchange of a shared secret. The authentication phase for a PPP session is optional. If used, the peer is authenticated after LCP establishes the link and chooses the authentication protocol. Authentication takes place before the network layer protocol configuration phase begins. Initiating PAP. So R1 sends its PAP username and password to R3. Note PAP is not a strong authentication. Using PAP, passwords are sent across the link in plain text, and there's no protection from playback or repeated trial and error attacks. So, okay. Authentication command. To specify the order in which CHAP or PAP protocols are requested on the interface, use the PPP authentication interface configuration command. Use the no form of the command to disable this authentication. PAP, CHAP, or both can be enabled. If both methods are enabled, the first method specified is requested during link negotiation. If the peer suggests using the second method or simply refuses the first method, the second method should be tried. Okay, this is an example of PAP authentication configuration. Okay, this is a CHAP authentication configuration. Okay, one router must match the username the other router has configured. So the password must also match, occurs on link establishment and can be repeated. So you can see here on host R1, the username is R2 and the password is someone. Okay. And in host R2, username is R1, which is the other router, and the password is same. Okay, debug command must not be used as a monitoring tool. Okay, meant to be used for a short period of time, but for troubleshooting. Can consume a significant amount of resources. Okay, debug command must not be as a monitoring tool. It's the same. Okay, let's go next. Okay. Okay, so let's try to make a basic configuration in a packet tracer. Okay. So here I have a packet tracer. Okay. So let's create a a router. Actually, I already did it, as you can see, but I'll show you how we did it. Okay, let's put two routers. Okay, and let's make a connection. Okay, let's turn this off. Auxiliary, no, serial. Okay, let's show it here. And let's go to serial. Okay. So let's configure the first router. Okay, so let's set the host name to R1. Okay, what else? Let's set the password, username and password. Username is so the username will be R2, the other Cisco, other router. So username R2 and password is Cisco. Okay, password Cisco. Yeah. Okay, let's go to the interface. Interface. It's 000. Interface S000. Okay. Let's put the IP address. IP address. Let's set let's say 10.1.1.1 255.255.255.252. Okay, and no shutdown. So change state interface. Okay, now okay, let's set the other router. Okay, let's power this on. Okay, let's go to the configuration. Let's change the host name to R2. Host name R2. Correct. And we set the username and password. Username. So this time we will use R1. Okay, and the password. Password is Cisco. Right. Okay. And then we go to the interface. Interface. Let's interface it. 000. Yes. 000. set the IP address. So we can use 10 dot 1 dot 1 dot 2 255 dot 255 dot 252. Okay, no shutdown. Enter serial to change state to up. R1 password Cisco. Okay, so as you can see, they're both up. Okay, then we set up the encapsulation. PPP encapsulation PPPP encapsulation PPP. Okay, encapsulation PPP PPP and authentication CHAP. So we use the CHAP authentication. Okay, PPP authentication encapsulation. Okay, CHAP, and let's set the clock rate. How much? 64. Okay. What else? Then we save. Save. Okay. Yes. Let's set the other one. Okay. So encapsulation PPP. So let's set the authentication PPP authentication CHAP. Okay. Clock rate, we set the clock rate 26400. Why is it showing like it? This clock rate. Choose the clock rate from the list above. I don't know what's running. Let's try copy and copy start. So okay. So let's wait for some time. Failed. Encapsulation PVP. Okay, it's up. Fail. Why is it failed? Oh, why is it failed? Did I miss something? because of the error here. DC interface. And that one, that one, that two. Then that one, that one, that two. Then that one, that one, that one. Encapsulation. PPP identification. Check. Okay, now it's become successful. I don't know why it took time. Okay, so now we're successfully configured the basic PPP configurations. Okay, so let's close this. Okay, okay, so let's continue. Branch connections. Now we move on to the branch connections. Okay, so uh, the Border Gateway Protocol, or BGP, is a routing protocol used between autonomous systems. This chapter concludes with a discussion of BGP routing and the implementation of BGP in a single home network. Okay, so cable components. Two types of equipment are required to send signals upstream and downstream on a cable system. Cable modem termination system, or CMTS, at the head end of the cable operator. The head end is a router with a database for providing internet services to cable subscribers. Okay. Service provisionals. This is a CMTS. Okay. So cable modem on the subscriber end. What is a DSL? Digital subscriber line. Means of providing high-speed connections over installed copper wires. Okay. So these are the homes with the DSL subscription connected to the ISP. And subscriber utilizing high-speed access network through DSL. Asymmetric DSL, or ADSL, provides higher downstream bandwidth to the user than upload bandwidth. Symmetric DSL or SDSL provides the same capacity in both directions. For satisfactory ADSL service, the local loop length must be less than 3.39 miles or 5.46 kilometers. Okay. So the figure shows a representation of bandwidth, space allocation on copper wires for ADSL, asymmetric DSL. Okay. The area labeled POTS identifies frequency range used by the voice grade telephone service. Okay, so POTS. Okay, the area labeled ADSL represents a frequency space used by the upstream and the downstream DSL signals. The area that encompasses both the POTS and the ADSL represents the entire frequency range supported by the copper wire. DSL connection. The DSL connection is set up between the customer premises equipment CPE and the DSL access multiplexer, or DSLAM, device located at the central office. Okay. Here is the DSLAM. The key components in the DSL connection: transceiver, usually a modem in a router which connects the computer to the teleworker to the DSL. So DSLAM located at the CO of the carrier. Okay, it combines individual DSL connections from users into one high capacity link to an ISP. So advantage of DSL over cable technology is that DSL is not a shared medium. Each user has a separate direct connection to that DSLAM. So factors to consider in selecting a broadband solution. Okay. Cable bandwidth shared by many users. Slow data rates during the high usage hours. Okay. So it means in like during office hours, or let's say during at nighttime when people are uh, most of the people are already at home and using their phones or laptops and browsing social media. So the the speed, you will notice the you know the speed, you will notice the what you call the change in speed. Okay, DSL limited bandwidth, that's distance sensitive in the relationship of the ISP central office. Fiber to the home requires fiber installation directly to the home. Okay. Cellular and mobile coverage is often an issue. So if you're in a remote area and you don't have a cell site near you, then you will have a problem browsing the net. So Wi-Fi mesh, most municipalities do not have a mesh network deployed. Satellite, it's expensive and, and it's too slow. PPOE motivation. PPOE can be used as all serial link, including those links created with the dial-up analog and ISDN modems. ISP often use PPP as a data link protocol over the broadband connection. So ISP can use PPP to assign each customer one public IPv4 address. PPP supports CHAP authentication, which we demonstrated earlier. Ethernet links do not natively support PPP. PPP over Ethernet or PPPoE provides a solution to this problem. So PPPoE troubleshooting. The following are possible causes of problems with PPPoE. Failure in the PPP negotiation process. Failure in the PPP authentication process. And failure to adjust the TCP maximum segment size. So these are the PPOE concepts. So PPOE creates a PPP tunnel over an internet connection. So this allows PPP frames to be sent across the internet cable to the ISP from the customer's router. Okay, this is the ISP. Okay, this router to the customer in a PC. Site-to-site VPN. Site-to-site VPNs connect entire network to each other. For example, connecting a branch office network to a company headquarters network. So in a site-to-site VPN, end hosts send and receive normal TCP/IP traffic through a VPN gateway. So the VPN gateway is responsible for encapsulating and encrypting outbound traffic. Okay. Okay. So dynamic multi-point VPN or DMVPN is a Cisco software solution for building multiple VPN. It is built using the following technologies. Next Hop Resolution Protocol or NHRP creates a distributed mapping database of public IP addresses for all tunnel spokes. Multi-point generic routing encapsulation, okay, or MGRE tunnels. An MGRE tunnel interface allows a single GRE interface to support multiple IP sec tunnels. IP security, IPsec encryption provides secure transport of private information over public network. So GRE introduction. Generic routing encapsulations. That's what's GRE means. It's a non-secure site-to-site VPN tunneling protocol. Developed by Cisco, GRE manages the transportation of multi-protocol and IP multicast traffic between two or more sites. A tunnel interface supports a header for each of the following: an encapsulated protocol or passenger protocol such as IP4 and IPv6, an encapsulation protocol or a carrier protocol such as GRE, a transport delivery protocol such as IP. So 5 steps to configure a GRE tunnel. Okay, so step 1, create a tunnel interface using the interface tunnel command. Okay, so in the configuration, you type interface tunnel and you put where you want to start. Let's usually 0. Okay. Configure an IP address for the tunnel interface. It's usually a private address. Okay, this one like 192.168 and so on. Specify the tunnel source IP address. Okay, so the tunnel source IP address is the port that usually it's the port going to the ISP. Okay, specify the tunnel destination IP address. It's the IP address of the router that you want to connect to. You want to tunnel to or tunnel with. Okay. Specify GRE tunnel mode as the tunnel interface mode. The tunnel source and tunnel destination commands reference the IP address of the pre-configured physical interface. Okay, we will try to configure, do a simple or a basic configuration of GRE tunnel. Okay, yeah. Verify GRE. Use the show IP interface brief command to verify that the tunnel interface is up. Yeah, show IP interface brief, and we put the tunnel. Show IP interface tunnel 0. Okay, so IGP and EGP routing protocols. IGP is used to exchange routing information with a company network or an autonomous system. Okay, an exterior gateway protocol (EGP) is used for the exchange of routing information between an autonomous system such as ISP. Border gateway protocol (BGP) is an exterior gateway protocol of EGP. Okay, so external BGP is the routing protocol used between routers in a different autonomous system. Internal BGP is the routing protocol used between routers in the same AS. Okay, autonomous system. Two routers exchanging BGP routing information are known as BGP peers. Okay, when not to use a BGP. BGP should not be used when one of the following conditions exist. If there is a single connection to the internet or another AS known as a single home, when there is a limited understanding of BGP. If you don't know too much of the BGP. Note, although it's recommended only in unusual situation, for the purpose of this course, you will configure a single home BGP. Okay. Okay. So let's go back to the GRE tunneling. Let's try this. Okay, so I have here a packet tracer file. Okay. So what we have here is we have a one router here as the ISP, and we have two routers where we're going to configure a GRE tunnel, and we have a switch between the PC. Those PCs, each router have a PC connected to it. Okay, let's try to ping this first. Okay, now functional ports. Okay, we need to configure. So we start with the router 1. Router 1. So we have the ports here. CLI. Okay, router 1. So we enter the configuration. Okay. So we configure the router 1 first. Let's change the host name. Let's change it to R1. R1. And okay, we go to, let's configure the IP address for this. Okay, so we go to the interface, which is G01, G01, G01. Okay, let's put 192.168.1.1. 192.168.1.1. Okay, and 255, the subnet, 255 that, 0. Okay, oh sorry, IP address 192.168.1.1. Subnet is 255.255.255.0. Okay, no shutdown. Okay, then we configure the serial port going to the ISP. Okay, so interface, what's the interface? 0 serial 000. Okay, so we put IP address. What's the IP address for this? Okay, 19.1.1.1.1. Okay, 252.255.255.2. Okay, 25S, we are here in S00, 255.255.255.252, and that one's same. No shit. Okay, and then we go to no, let's set the IP route first. Okay, IP route. So the IP route, okay, should be 0 0 dot 0 dot 0 dot 0 0 dot 0 dot 0 dot 0, and okay, so the route is going here on the ISP. So let's put the ISP IP address 10.1.1.2, correct? 10.1.1.2, 10.1.1.2. Okay, IP route. Okay. Then what else? We set the tunnel. Okay, the interface tunnel. 0. So it start with 0, interface tunnel 0. Okay, and wait, the tunnel 0. We put the IP address for the tunnel, which is this one. Okay, so we're now inside the tunnel 0, and we IP, put the IP address. The tunnel's IP address is 192. From this router is 192.168.10.1. Okay, 192.168.10.1, 255.255.255.252. Okay, 252. 218 is correct. Yeah. Okay. Then we set the destination, the source, tunnel source, tunnel source. So the tunnel source is this this one. This is the one. This is the one will provide the tunnel, the connection to the ISP. So we put S000, because we will connect to the tunnel through here. Okay, and the tunnel source, tunnel destination, destination is, so we're going to put this one. These are destination tunnel 192.168.10.2. Okay, say the 10.2. So that's a destination. Destination. Wait, no. We have to put the this one. We need to put, what's the IP? This one. Okay, 10.2, the 2.1. Okay. Okay. 10.2.2.1. Okay, 10.2.2.1. That's the destination. Okay, then let's exit. Okay, exit. So let's go to the next. Let's set up the second router. Okay, and configure. Let's configure the second router. Let's change the host name to R2. Okay, yeah, R2. Okay, then let's set the serial port. Okay, let's go to the interface of the serial port. It's the interface port 001. 001. Okay, correct. Okay, so now we're inside the interface of the serial port 1. Okay, then we put the IP address. Okay, IP address. Okay, IP address is, which is this 10.2.2.1, 10.2.2.1, 10.2.2.1. Okay, 2.2. Okay, shutdown. Okay, now what else? Exit. Put the route. IP route is 0 0 0 0 0 0. Okay, so the IP route is going here. 10.2.2.2. 10.2.2.2. Okay, IP route. So that's the IP route. Okay. Now let's set up the tunnel. Let's check first. Interface number 0. We can use 0. Okay. Now let's put the IP address of the tunnel. IP address is 192.168.10.2. 192.168.10.2. 192.168 the 10.2. I put the enter. Okay, 192.168.10.2. 2.5.2.5 but 2.2. Okay. Yeah, so we already set the IP address of the tunnel. Let's set the tunnel source. Okay, tunnel source. So the tunnel source is this one, SE001. S001. Okay, that's the tunnel source, and the tunnel destination is this 10.1.1.1. 10.1.1.1. 10.1. Okay, 10.1.1.1. Okay, exit. Okay, exit. Let's show IP. Let's check the IP. So for the serial going to the ISP, we have the IP tunnel. We have successfully set the tunnel to, okay. So serial and tunnel, and we forgot, the IP address, this one. Okay, so where is it connected? G01. Okay, config. Okay, interface G01. So what's the IP address of G01? 192.168.2.1. Okay, IP address 192.168. What's 1? 2.1. 2.1, 2.5.2.5.2.5.0. Okay, what else? Okay, 01 is connected here. Okay. Now we need to set the IP of this. So now we're in the ISP. Let's change the route. Okay. Config. Okay, host name is ISP. Okay. Then we go to the serial. Okay. Interface S000. Okay, then we set the IP address to 10.1.1.2, 10.1.1.2, 255.255.255.252. Okay. Okay. And we have to set the other one. So we go to interface. Yes, 001. Okay, S001. So let's IP address to 10.2.2.2, 255.255.255.252. Okay. 255. Okay, so now it's having the green light. Okay, needs to up. Let's try to ping. Ping. Do that. 168.10.2. Okay, now we are successfully connected through tunnel. Okay. Okay. So let's try this. If we're able to connect. Okay. So we have successfully connected through the tunnel. Okay. Let's check if trace route 192.168.10.2. Okay. So as we can see, okay, the route didn't go through here, but it goes directly to here. Okay, trace route. Okay. Yeah, so we have successfully configured a tunnel between this between these routers. Okay, so we need to set the IP address. Okay, default gateway is 192.168.1.1. IP address for this is 192.168.1.5. Okay, let's configure this. Okay, 192.168.2.5. 2.5. Subnet mask. Okay, default gateway is okay 192.168.2.1. Okay, correct. Okay, let's try to read. Where is it? 2.168.1.5. Okay, successful. And this. Okay, successful. Okay, let's we forgot something. We forgot to set the OSPF. Oh, yeah, router OSPF. Okay. So let's go to config. Okay, so router OSPF 1. Router OSPF 1. Okay. So we need to configure the network. Network what's this? Network 10. 192.168.10. That okay. 192.168. That 10. Is it 10? That 1.0. I had to say that 1.0. Okay, the 10 is 0. That's 0. That's 0. That 255 area 0. Network. Network 192.168. Oh, sorry, the 10.0. Okay, so exit. So SOS, we subset OSPF. We need to set router or SPF1. Okay. Set this to 1. Okay, exit. So exit. Let's show IP route. Then that they're connected to serial. One connected to serial 0. Need to do gigabit. Then that. Okay, let's set the other one. router OSPF1. Okay. We put the network 192.168.10 dot 0 0.0.0.255 area 0, correct? Okay. Okay, then we put this IP range. Okay. Okay, network 192.168.2.0 and 0.0.0.255 area 0, 255 area 0. Okay, and exit show IP route. Okay, so let's try to ping from this PC to this PC. Okay, which one we're going to ping? Ping 2.5 192.168.2.5. Yes, so it's replying. Okay, yeah, so we have successfully connected. Okay, trace route. Is it trace route? Ping. So not tracer. It's trace. If it's really using the tunnel. So we ping this 192.168.2.5. 192.168.2.5. Okay, let's see. So from this PC 192.168.1 connected here. Okay, and directly from here that 10.2, that one, he goes to, where is it, that 10 192.168.10.2. so he didn't go here in the ISP and he go through the tunnel from 192.168.10.1 or 192.168.1.1. he go to the tunnel through 192.168.2.10.2. Okay, so we have successfully uh, configured a basic GRE tunnel. Okay, let's save the file. Save. Okay, then let's proceed to the next topic. Yes, of course. Okay. Yeah. So we have successfully configured GRE tunnel. Okay. So let's proceed. So where are we now? Okay, so now we proceed to access control list. This chapter begins with a review of ACL and standard IPv4 ACL configuration. The chapter then explains how to configure and troubleshoot extended IPv4 ACLS on a Cisco router as part of the security solution. Okay. So the standard ACL operation and configuration review. Okay. So an ACL contains a sequential list of permitter deny statements known as access control entries or ACEs. ACEs are also commonly called ACL statements. IPv4 ACEs includes the use of wildcard, mask, which are a string of 32 binary digits used by the router to determine which bits of the address to examine for a match. Okay, so in ACL, you can configure one ACL per protocol. To control traffic flow on an interface, an ACL must be defined for each protocol enabled on the interface. So one ACL per direction. ACL control traffic in one direction at a time on an interface. Two separate ACLs must be created to control inbound and outbound traffic. One ACL per interface. ACL control traffic for an interface, for example, a gigabit internet. Extended ACLs can filter traffic by examining TCP port numbers. Common TCP and UDP port numbers include like this. You can see from the list, port number 20, 21, 22, 23, and so on. We have TCP, UDP, TCP. Okay, so for port 20, we have FTP, file transfer protocol, or if it's 21, it's also file transfer protocols. Okay. To help maintain how an ACL operates, I refer to the decision path used to filter the web traffic. Okay, so you can see from here. Okay, standard ACL operation and configuration. ACL has been configured to permit web access to users from network A, but denied all other networks to network A users. Deny HTTP access to users from network B, but permit network users to have all other access. Okay. Standard and extended ACLs can be created. Okay. So extended ACL should be located as close as possible to the source of the traffic to be filtered. See from the diagram, extended ACLs are usually placed near the source, and ACL are usually placed near the destination. Okay, a standard ACL will be configured to block all traffic from 192.168.10.0/24. Okay, the standard ACL should be applied close to the destination, therefore could be applied outgoing to R3 router 3G00 interface. So from here you can see the implementation of IPv ACL. Okay. The full syntax of the standard ACL command, as you can see from the right. So standard ACL operation and configuration review standard IPv4 ACL implementation. For example, permit all address in network 192.168.10.0/24. Use the no access list 10 command to remove an ACL. Use the remark keyword for documenting an ACL to make it easier to understand. Okay. An IPv4 ACL is linked to an interface using the following interface configuration mode command. Okay, access list, permit. So here are the examples of the access list command. An application can be specified by configuring either the port number or the name of a well-known port. So in this example, FTP traffic from subnet 192.168.11.0 going to subnet 192.168.10.0 is denied. Okay. But all other traffic is permitted. So FTP utilizes two port numbers, TCP port 20 and 21. So therefore, two ACEs are required. So the example used the well-known port names FTP and FTP data. Okay. So without at least one permit statement in an ACL, all traffic on the interface where that ACL was applied will be dropped. Name extended ACLs are created in the same way that named ACLs are created. In this example, two named ACLs are created. So surfing permit users on the 192.168.10.0 by 24 networks to exit going to ports 80 and 443. Browsing enables return HTTP and HTTPS traffic. Okay. So this is how you configure extended IPv4 ACL. So the show IP interface and the show access list command can be used to verify the content of extended ACL. The output and sequence number displayed in the show access list command output is the order in which the statements were entered. Unlike standard ACL, extended ACL do not implement the same internal logic and hashing functions. So host entries are not automatically listed prior to the range entries. The show IP interface command is used to verify the ACL interface on the direction in which it is applied. The output from this command includes the number of the name of the access list and the direction on which the ACL was applied. It is beneficial to consider how an inbound and outbound ACL is processed. Inbound ACLs operates as follows. If the information in a packet header and ACL statement match, the rest of the statement in the list are skipped and the packet is permitted or denied as specified by the match statement. If a packet header does not match an ACL statement, the packet is tested against the next statement in the list, and this matchmaking process continues until the end of the list is reached. So at the end of every ACL is a statement is an implicit denial. Any statement can because of this statement because an ACL should have this one permit statement on it. Otherwise, the ACL blocks all traffic. So outbound ACLs operate as follows. The routers check the routing table to see if the packet is routable. The router checks to see whether the outbound interface is grouped to an ACL. If it is, the ACL is tested by the combination of ACEs that are associated with the interface. So based on the ACL test, the packet is permitted or denied. So standard ACLs only examine the source IPv4 address. So the destination of the packet and the ports involved are not considered. The Cisco IO software test addresses against the ACL ACEs. The first match determines whether the software accepts or rejects the address. Because the software stops testing the conditions after the first match, the order of the condition is critical. If no conditions match, then address is rejected. So common ACL errors are entering ACEs in the wrong order or not applying adequate criteria to the ACL rules. So in this example, the host 192.168.10.10 has no telnet connectivity with the 192.168.30.12. Deny TCP as you can see from this. Okay. So the host 192.168.10.10 has no connectivity with the 192.168.30.12 because statement 10 denies host 192.168.10.10. Therefore, the statement 20 can never be matched. Statement 10 and 20 should be reversed. So here's also another example. So now we go to the conclusion of the access control list. So by default, a router does not filter traffic. Traffic that enters the router is routed solely based on information within the routing table. An ACL is a sequential list of permit or deny statements. The last statement uh, of an ACL is always an implicit deny statement which blocks all traffic to prevent the implied deny any statement at the end of the ACL from blocking all traffic. The permit IP any statement can be added. Okay, and so on. So this is the end of my video. Thank you for watching, and God bless.